So this is I'm just going to work through this worksheet on continuity. This is the worksheet I hand out to my class earlier this week, and just want to talk through it. So it says, I want to be clear on the directions here. It says state whether or not each of the following functions are continuous. So, and if not, state where the discontinuity occurs and which part of the definition fails. Also describe the type of discontinuity, removable, jump, asymptote, etc. Okay. So basically, when we're looking at a function like this, we're looking for discontinuities, and the discontinuities often occur when the bottom of the fraction is 0. And you notice on the first equation that x squared plus 1 is the bottom of the fraction. There's no way you could make that 0, because when you square something, it becomes positive, and a positive number plus 1 will never equal 0. So we know that this is a continuous function. Right? Now we go to the next one. Often it's a lot easier to see these things if it's factored. So first thing I'm going to do is factor this. 2x there. X looks like a 1 and a 1. And we want that to be negative and that to be positive. Change my thing here like that. Okay. And when we do that, let's try that again. That looks awful. So that would be x minus 1 on top, and 2x plus 1 times x minus 1. And so anyway, notice that what makes the bottom 0 is, so there's a discontinuity at 1. So a discontinuity at x equals 1, and a discontinuity at x equals negative 1/2. Now, because we talked about this in class, because these two, the x minus 1 is a factor of the top and bottom, that means that x equals 1 is a whole or removable discontinuity. So we can call this removable right now, removable. But it also means that if it's removable, it means there's a hole there. That means there will be a limit as x approaches 1. So the part of the definition fails is that f of 1 does not exist. On the second one, there's actually a vertical asymptote there, so that means actually there's none of the parts of the definition pass. So you could say f of negative 1/2 does not exist, or you could say the limit as x approaches negative 1/2 does not exist. And this is an asymptote. Okay. Moving right along. So on this one, again, I would factor it first. The 2x plus 3 is already factored. The bottom would factor into x and x and 2 and 3. We want a negative 3 and a positive 2. So notice there's nothing will cancel at the top, so both of those discontinuities are going to be asymptotes. So we have a discontinuity at x equals negative 2 and one at x equals 3, and neither one of them, in both cases, none of the parts of the definition pass. So I'll just pick this one. It's easiest to write. And they both are asymptotes. Asymptotes. Asymptote. Okay. And so these are, the first page here are very similar. So I'm going to go ahead and move on to a different one. For example, and one of these piecewise functions. So in this case, I notice that there's a problem with this function. Okay, so first of all, x equals 3 is a problem. But notice that's the borderline. I think we talked about this one in class. That so there is a hole at x equals 3. So the question is, did this plug it or not? Because they basically what they said, recognize there's a hole in 3 at x equals 3. They decided to define 3. And so the question is, does the 8 plug the hole? And so what we're going to do is we have to find out where that hole is. So, and we can find that by factoring this out. X minus 3 times x plus 3 over x minus 3. And if we just cancel out the hole and then plug in 3, we get 6. So the 8 doesn't plug the hole. So we have a discontinuity at x equals 3. Discontinuity at x equals 3. And the limit does exist there. But the reason why it fails the definition is because, once again, and f of 3 exists. So the reason why it fails the definition is that f of 3 is not equal to the limit of f of x as x approaches 3. And so there is a limit. It's 6. We found it up here. There is a value. F of 3 is 8. It's right there, but 6 and 8. So in other words, this guy is 8 and that guy is 6. And those clearly do not equal. And so we would call this a removable. This is basically just a hole. Now in number 10, both the separate two definitions are continuous, so we don't have to worry about anything with either one of those functions. So we only have to worry about where they come together. So the question is, do they meet? So when I plug in 2 here, I get 4 minus 3, which is 1. When I plug in 2 here, I get 4. So they do not come together. So what's going to happen just do a quick little sketch here. At x equals 2, we know this one's going to be equal to, 1, I think I said. Is that right? Yeah. 4 minus 3. Yeah. So that's going to be right there. And then at for x squared, when I plug in 2, I get 4. So it's going to end up being, there's 1, 2, 3, 4. It's going to be a little open circle up here. So you notice this will be coming in as a line. Something like that. Oops, I missed. This will be coming in as a line. Something like that. And this will be a part of a parabola, so it'll keep going off like that. But the point is, as the two come together, as you approach x, or as x approaches 2 from both sides at the same time, they don't meet, they disagree. So this would be a discontinuity at x equals 2, and it's because the limit of f of x as x approaches 2 does not exist. Or I guess I should just write equals does not exist. Equals does not exist. Now this one, because you're coming in at 2 different places, it's like you have to jump to get up to there. So this is what is called a jump discontinuity. And I think I'll do one more, do number 12. So we want to probably plug in some numbers to find out what's going on here. When you plug in something bigger than 3, like say 4, so let's do f of 4, you're going to get 4 over 1, aren't you? If you plug in something, and of course you plug something bigger, if you plug in 5, you'll get 5 over 2. If you plug in 6, you'll get 6 over 3. It'll stay positive. And it'll be a nice continuous graph. But if you plug in something less than 3, like if you plug in 3, f of 3, we get undefined, don't we? Now, what happens immediately to the left of 3? So if I'm plugging in something smaller than 3, notice when I plug something smaller than 3, I get a negative number. So like, for example, f of 2, I get a 2 over negative 1, which would be a negative 2. So you start plugging in some numbers and you realize there's some strange things going on here. So in a situation like this, it might be best to graph it. So if you plug it into your graphing calculator, what you discover is it is a very funky looking equation. It has a little swoopy thing like this with an asymptote there and there. And then it comes down like this. And it comes up like this. And so you can see there's some discontinuities and we can figure out what that would be. That would be obviously 3. And the other one obviously would be negative 3 because of the absolute value, because absolute value of negative 3 is 3 also. So when I plug in 3 or negative 3, it gives me, makes me divide by 0. So in the end, let's come over here. My discontinuities would be x equals 3 and x equals negative 3. And the reason is because f of 3 and f of negative 3 do not exist. And those are called asymptotes, both of them. Oh, I guess I will do one more. I want to do one of these down here where you have to figure out what A is. So I think we didn't do this one in class, number 14. So this is asking you to make this thing continuous. And again, the idea is that this function by itself is continuous, this function by itself is continuous. So the only problem of discontinuity would be where they come together. So we have to make ax squared equal to 2x plus a when x is 2, because that's where they come together. So if I plug in 2 for x, I get 4a is equal to 4 plus a. So then if I subtract a from both sides, I get 3a is equal to 4, which means a is equal to 4/3. So that tells me if I make a equal to 4/3, this would be a continuous function. So basically making the parabola and the line connect. All right.